Hi, my name is Kush, and today I'll be talking a little bit about simulating waves in plasmas. And before we begin, I'd like to thank Dr. Swistak and Professor Drake for spending a lot of time with me on this project, giving me some great opportunities. So getting to the research, sometimes in space plasmas, a type of plasma wave called a Whistler wave forms. Let's break that down. First of all, what is a space plasma? Well, the space plasmas we're interested in include plasmas like the solar wind, as well as plasmas that can be found in the intercluster medium of galaxy clusters. And as for the waves themselves, well, they're right circularly polarized, and their names comes from the sound they make when you pick them up on Earth's radios. So I have an audio clip of that I'd like to play. But don't worry, if you hear space lasers outside your house, it's just a Whistler wave. So the reason we're actually interested in Whistler waves are that previous literature has shown that they're thought to maybe control how energy flows in a galaxy cluster. So we're interested in figuring out how Whistler waves might actually do that. And the way we will figure that out is using what's called a test particle simulation. So let's break that down as well. Previous simulations have been what's called a particle and cell simulation. Now that's a simulation where particle trajectories and energies are tracked over all space, but quantities like electromagnetic fields that control these particles are calculated at grid points. Now, this has the advantage of getting all the physics right and making sure all the equations are self-consistent, but it comes with a huge computational cost, and so previous simulations have been limited to 2 dimensions. Now, our simulation is what's called a test particle simulation. In this simulation, electromagnetic fields, as well as the particles, are tracked over all space, no need for grid points. But it does have the disadvantage that the particles don't give feedback on the waves that control them. Now, our simulation uses a numerical integrator that's called the Boris algorithm. This type of integrator is really nice because in the zero wave case, when we don't have a wave in our system, it preserves energy almost perfectly. So actually, what do these waves look like mathematically? Before we can code up a simulation, we need to know what they look like. Well, we can start with some equations here, 2 of which are Maxwell's equations, the first 2. And we can make a couple of approximations that are useful computationally. And these approximations are justified by this plot here. Oops. So this plot shows the relationship between 2 parameters that sort of fall out from these 4 equations. And the red curve is the exact relation. The blue curve, the blue pluses, are the relationship after making these 2 approximations. And we can see that in this regime that we care about, the approximation is almost perfect to the exact. So indeed, these approximations are justified. And after solving these equations, you can come up with a useful dispersion relation, which relates the frequency and wave number of the wave, along with a couple of plasma parameters thrown in, getting the units right. So before actually delving into the real meat of the results, I'd like to make a quick terminology note that you'll see. So we're all familiar with momentum. Well, canonical momentum is a form of momentum that includes contributions from the electromagnetic fields. And from solving the Hamiltonian that governs our system, we would expect conservation of canonical momentum along directions where there is no wave, what's called invariant directions. And we indeed see that in our simulation. So in the one wave case, we have a wave in xz. There's no wave in y, so y is invariant. And indeed, canonical momentum in y changes less than 1% over the course of our simulation. But once we add a second wave, that picture changes. We see the red curve here, that's the 2-wave case. It rises hundreds of percents, whereas the 1-wave case, plotted here in blue by comparison, is almost flat on these axis scales. Now moving on to particle motion, we see that in the 1-wave case, we have some bounded motion in the xy plane that's perpendicular to the strong guide field in our simulation that sort of governs our system. And this motion can be explained by sort of 2 reasons. The motion in x, the bound in x, can be explained by that canonical momentum conservation I was discussing earlier, whereas the bound in y can be explained by that strong guide field in z. But as soon as we add a second wave, again, the picture changes dramatically. So this plot is of the average x squared plus y squared of the particle. That's basically the radial distance of the particles from where they started in the xy plane. And we see that instead of being bounded like before, they're actually streaming and diffusing unbounded in a linear fashion. Although it is streaming away from where it started generally, the particles actually don't gain energy very much over time. And that's pretty interesting, something we'd like to investigate more. So if there's one takeaway point, it's that one wave leads to unbounded motion in the xy plane. Two waves, you get, one wave is bounded motion, two waves is unbounded, and that can help inform our future simulations because clearly there's some interesting physics to be had by introducing that third dimension, that YZ wave. So we'd actually like to investigate this more with a 3D particle and cell simulation and investigate how these trajectories change when we add more and more waves, which is what I've been doing more recently, and that's here. Before we were having sort of this constraint along a line for the two-wave case in the xy plane, but as soon as we add more and more waves, this sort of breaks that constraint, and now we're allowed to have more sort of diffusive behavior in the xy plane. So thank you for listening.